Hi friends and my dear students, a very warm welcome to all of you for my session today. In today's session, let us talk about packing efficiency. In fact, friends, you'll understand this topic better if you have watched my previous video about close packing in crystals. Please do watch that video and then get back to this topic, okay? But yet, I would like to give you a quick recap for you guys, right? In the previous video, we saw that the constant particles, right, in the form of spheres, and these spheres were packed in different dimensions, starting from 1 dimension, 2 dimension, and all the 3 dimensions, resulting in various types of close packed structures. In fact, we saw 2 types of structures, that is CCP and HCP. Do you remember? That is cubic close packed and hexagonal close packed, right? So we also saw that though these spheres were actually closely packed, touching each other, right? And though they were arranged in different types of arrangements we saw, yet between these spheres, we saw some empty spaces called voids. In fact, we saw 2 types of voids, that is tetrahedral voids and octahedral voids, right? That means, friends, for packing to be more efficient, I am trying to repeat this once again. In fact, I said this in the previous video also, and here I am trying to repeat for you guys. For packing to be more efficient, right, out of the total space available in the crystal lattice, maximum space should be occupied by the spheres or the constant particles, right? If at all there is any empty space left over, it should be actually very less. Then only such a packing will be more efficient, and that represents packing efficiency. So what is packing efficiency? In other words, out of the total space available, only a fraction of the space will be filled or occupied by the constant particles. And how much filled is a fraction, and that is actually represented as packing efficiency. But since this fraction is a very general term, let us make it very specific, and hence packing efficiency is usually expressed in terms of percentage. So my dear friends, packing efficiency is nothing but, yes, the percentage of total space filled by the constant particles. Okay? Right. I hope you understood. But why are we talking about packing efficiency? Once again, to emphasize the fact here, it's a percentage of the total space filled. So out of the available space, if more space is filled, obviously packing efficiency will be more, and such a crystal lattice will be more stable. But we saw different types of packing arrangements, isn't it? And once the packing arrangements are different, the spheres are packed in different ways, and hence the space actually filled in different packing arrangements also will be different. That means, friends, packing efficiency will not be same in all types of close packed structures. So let us now take up different types of structures and calculate the packing efficiency, and also see which is more stable by comparing the packing efficiency. And mind you, my dear friends, definitely you will get a question from this topic, especially for your board exams. There they'll ask you to calculate the packing efficiency of any one of the structures which I'm going to explain right away. Okay, to begin with, let us take up packing efficiency in simple cubic lattice. For that, take a look at this simple cubic unit cell. Can you see the spheres are actually present at the 8 corners? And if you carefully observe, these spheres are in fact touching each other, isn't it? Yes, along the edges, if you watch carefully, 2 spheres are in contact with each other. That means 2 neighboring spheres, right, which are closely packed, are in contact with each other along every edge. 2 along each edge. Are you there? Fine. Now let us focus upon only 4 spheres that are facing us. Okay, very good. Now, in this image, you can see those 4 spheres here. That is 1, 2, 3, and 4. And these points, that is A, B, C, and D, represent the centers of those spheres, or we can say the corner positions of the simple cube, or of the perfect cube what we get here, isn't it? Fine. When we join these 4 points, what do we get? Of course, the edges, right? Here you may see this as one perfect square, but actually this is representing the face out of the 6 faces of the cube because of the 8 spheres touching each other at the corner positions, right? Very good. Okay, so this being one of the faces, we know every face has 4 edges. As you can see, AB is one edge, BC is one edge, CD is one more edge, and DA is the 4th edge. So if you have an edge, the edge should have a length, and that is called edge length. So let us assume the edge length as A. And just now I said it is a cube, and a perfect cube should have all the edges same, and their edge lengths also will be equal. Therefore, AB equal to BC equal to CD equal to AD equal to A. Means all edge lengths are same, that is A. And just now I said we have considered the constant particle as a sphere, right? So sphere will have obviously a radius. So let us call this portion as the radius of this sphere. But, okay, this is the radius of another sphere, isn't it? Therefore, now we can relate what? A and radius like this. How? See, this from this point to this point, this is A. So A is now equal to 2 times R, isn't it? Therefore, now I can say A and R are related as A is equal to 2R. But you may be wondering, why am I talking about A first? I should teach you how to calculate packing efficiency, isn't it? Why A has come into picture? Yes, I'll tell you the relationship there. Don't worry. Actually, my dear friends, packing efficiency, in short, if I say PE, I try to explain it in the form of a statement, but mathematically, I can actually show in the form of a formula, right? And that is, PE is given by the total space available. When I say total space available, I am not talking about the entire crystal lattice. Here I am taking only that smallest 3-dimensional portion of the crystal lattice. What is that? Unit cell. Okay, if I can find the packing efficiency in one unit cell, it applies to the entire crystal lattice as well. Okay, so keeping that in mind, let me tell you what is packing efficiency, right? Packing efficiency is given by the formula. So here you will write total space available. When I say total space, it represents the actual volume of the unit cell. So either you can say total space or you can say total volume, right? But of what? Because we're talking about 3-dimensional space, and the quantity that represents the 3-dimensional space is nothing but volume. So total volume of what I said? Unit cell. Whichever unit cell you have taken here. What do I mean? The type of unit cell you have considered here in turn depends on the structure we are dealing with. Okay, my dear? Very good. So total volume of the unit cell actually available. Out of that, what volume or what space is filled? Space means volume. Volume of, filled I said. Filled by what? Filled by the spheres. Some number of spheres will be filled, isn't it? So let us call this n spheres. So let us say n spheres are filled or occupied. But each sphere will have a volume. So what is the volume of all those spheres? So that will tell you the volume, okay, or the space actually filled, right? But this is expressed in terms of percentage, I told. Therefore, into 100. Oh, into 100. Yeah. To understand this big formula, okay, I'll give you a small trick. Okay, very simple. We can say like this. out of the total volume of the unit cell, if this is the volume, some volume, okay, of n spheres is actually filled, then out of 100, how much? Is it clear? Just cross multiply, unitary method, then you'll get the same formula. 100 into this plus volume of n spheres divided by this one. What is that? Total volume of the unit cell. This is how you get the formula. So you don't have to by heart this. If you understand the concept, you will get the formula. Generally, people by heart the formula, but I don't want you to do like that. Understand the concept, how exactly we arrived at the formula. Once you know the formula of packing efficiency, it will be very easy to calculate, right? So in that, you should first of all find the denominator. Denominator is total volume of unit cell. Here, unit cell belongs to simple cubic lattice, which is representing a perfect cube, right? And we know the formula of volume of a cube is a cube, that is edge length into edge length into edge length. Yes. Therefore, now let's get back. We had to now find out what is A. Once we know what is A, it will be easy for us to now find out the volume of the unit cell. Okay. Yes, that's what I said. Volume of the cubic unit cell is given by the formula A cube. In place of A, I can now substitute 2R. Therefore, it's 2R whole cube, which is nothing but 2 cube means what? 2 into 2 into 2, that is 8. So this comes to 8R cube. Are you clear? So we got the denominator part of the formula. What is the numerator part? Yes. A simple cubic unit cell contains one atom. In other words, one sphere. This also I have taught in yet another video how to calculate the number of atoms per unit cell. There is a simple cubic unit cell and the number of atoms belonging to that, okay, simple cubic unit cell is 1. Just try to remember or please watch that video and get back here. So it's actually 1. And one atom means it's a sphere and the sphere will have a volume. That means volume of the sphere now. Okay. The sphere means how many here? I said n spheres. Here n is equal to 1. Keep that in mind. See the structure properly. What unit cell? Then only you can remember this. Okay. You cannot put whatever number you want. So volume of one sphere will be, what is the volume of sphere in general? 4 by 3 pi r cube, right? It is 1 only. Therefore, 1 into this is same. Okay, friends. Now we got the numerator part also, right? So, shall we proceed now? Yes. As I told you, this is the formula. So, what is the numerator we got? 4 by 3 pi r cube divided by volume of the cubic unit cell we just got. Isn't it? 8 r cube into 100. So, further simplification, 4 by 3 pi r cube into 8 r cube, right? Here also we'll put an into. So, we'll try to cancel out the common terms. R cube gone. 4 ones are 4 twos are. Therefore, now you got pi by 6, isn't it? 3 twos are 6 into 100. If you further calculate, you'll get 52.36%. You can approximate this to 52.4%. So what is the packing efficiency in the case of simple cubic lattice? Yes, it is 52.4%. That means out of 100 units of volume available, only 52.4 units of volume are filled. Okay, that means what is the wastage here? In other words, what is the empty space? Empty space will be available space minus the space filled or packing efficiency. This 52.4. Will that come to 47.6? Isn't it? Yeah. Yes. So 47.6 is not the packing efficiency, it is an empty space. Packing efficiency is 52.4. Are you clear, my dear? So if you're clear with this, we'll proceed with the next structure. Are you ready? So shall we take up the next structure now? Yes, and that is body-centered cubic structure, BCC in short. Take a look at this image, please. Yes. Basically, this is a cubic system, no doubt. But since it is BCC structure, we know in a BCC unit cell, you will have the spheres or the particles, okay, both at the corner positions as well as at the body center, that is at the center of the body of the entire unit cell. So here we have highlighted only three fellows or the three spheres, two at the corners around this point F and A, and one, that blue, right, sphere is in the center of the body of the unit cell. But you may be wondering, why am I not showing the other corner fellows? In fact, friends, in BCC unit cell, even if you have, okay, two spheres like this at the corners, they don't touch. It's very important. Unlike in the case of simple cubic unit cell, we saw both were touching each other along the edge. Remember? Therefore, we took A as 2R. But here, they are not touching each other. But where are they touching, if you ask? Right? They are touching along the body diagonal. If you join A and F, it is a diagonal that is passing through the body of the unit cell. Therefore, AF actually it is the body diagonal. Only along the body diagonal we can see three spheres in contact with each other. What are those? Two at the corner positions and one in the body center. Okay, which I would like to show you in this way. So shall we join them now? Yes. As I told you, AF is the body diagonal. But why did we join FD? And what does FD represent here? Okay, you know A is the edge length. I need not tell you. That's why I did not specify. Because A is the edge length we have considered in the previous case also. Fine. In fact, this is A means all the edges will have the same edge length A because this is a cubic system. Please remember. But why should we take up this B? And what is this B here? B is FD. And FD is once again the diagonal, but diagonal passing through the face. In fact, that face is the bottom face, this one. I'm talking about this face. Okay, so this is B, that is the face diagonal. I know your doubt. Ma'am, you're teaching how to calculate packing efficiency. And in the packing efficiency, the denominator is the volume of the unit cell. Right, to find out the volume of the unit cell, we should know the edge length because the formula is A cube. So, directly go to A. Why are you talking about C, B, this body diagonal, face diagonal, isn't it? That may be your doubt. Please hold on, my dear friends. It's my humble request because here we cannot find A directly. The reason is, once again, I'm telling the spheres along the edge length are not in contact with each other. Therefore, in this particular case, A is not equal to 2R. Let me make that very, very clear. Don't think A is always 2R. It was 2R in the case of simple cubic lattice because the spheres were touching each other along the edge. I'm repeating once again. Don't worry. Be with me. That's it. Right? So, to arrive at A now in this case, actually we should do certain things. Right? To find out A, okay, this is also A, right? If you consider this triangle, it's a right angle triangle. In fact, you can find B if you apply what theorem? Pythagoras theorem. But do you know what is B? B is an unknown. So we have to find B first. To find B, you need to take up this triangle now. That is AFD. If you take that triangle, knowing C, that is AF, and what is AD? A once again, we can find B. That means, friends, to arrive at A, we need to consider two triangles as I just now said. What are they? Let me highlight that once again for you. AFD, okay, and let me take one more color. EFD. First, we'll take up the triangle AFD. Before that, what is AF given as? C, I told you. Let's call it as C, that is a body diagonal. And C, don't you think now it is equal to 4R? Why? Because all these three spheres are touching each other. And if you consider R as the radius of each sphere, so these are the radius of this sphere. These two are R's. That means from this point to this point, it represents the diameter of that sphere. That is nothing but 2R. And this is the radius of the third sphere at the corner. Therefore, isn't it R plus R plus R plus R? That is 4R. Therefore, here the body diagonal is AF, that is C, and C is actually given as what? Yes, I told you FD is the face diagonal, all that we know. So C is equal to 4R. It has equation 1. Fine, my dear. Now we have to find out what? B, that is FD. To find FD, I told you we have to apply Pythagoras theorem. Okay. In this triangle AFD, okay, my dear, what is the actually the hypotenuse? Yes, that is C, right? AF square. So, hypotenuse square, that is AF square, is equal to sum of the squares of the other two sides. What are the other two sides? AD and FD, right? So we have AD square plus FD square. Let us take only AF. Then we can take square root of this. In place of AD square, can I put A square? We'll retain FD square as it is, but it's actually B square. Okay, we'll write as FD square. Okay. Now, in place of AF, I can put what? Actually 4R. If you want, you can put B square here. A square plus B square. Now we have to find B square or FD square. For that, what should we do? Consider the next triangle, that is EFD. Again, applying Pythagoras theorem, right? What do we get now? Look here. This is the, which is the hypotenuse here. So friends, to find FD, let us consider the next triangle, that is EFD. Okay, but before that, let's call this as equation 2. Shall we proceed now? Yes. So, by considering triangle EFD, we can find FD, that is B now. For that, once again, we have to apply the Pythagoras theorem. Here, FD square will be equal to EF square plus ED square, isn't it? But what is EF? EF is yet another edge length. Therefore, there is also A. Please remember that. Very good. Don't think EF is lesser than ED. It's just a diagram, but actually it's a perfect cube. Therefore, all edge lengths are same. Okay, my dear. Therefore, let's now quickly write EF square plus ED square, right? So, what is FD from this? Square root of this. In place of EF square, can I put A square? Yeah. ED square is also A square. What is A square plus A square? Under root 2A square. So, this can be written as root 2 into A square under root, or square root of A square. So, root 2 will retain as it is. A square and square root of A square. Means square root of A square is nothing but A, isn't it? Hope you know that. Therefore, this can be written as A root 2. What is this A root 2? LHS is FD. Now, shall we substitute for FD? Yes. Substituting for FD in equation 2. We'll go back to equation 2 now. Yes, this is equation 2. Here, we'll substitute for FD. What will we get? What did we get FD as? A root 2, isn't it? What is FD square now? Squaring this, what should you get? A square. Root 2 whole square is 2. Therefore, it is 2a square. Okay. That's what I'm going to write it here. 2a square. A square plus 2a square will be how much? Yes? Yes, my dear, you must have done by now. This is 3a square, right? That is AF. Under root. Okay, let's call this as equation 3. If you compare equation 1 and 3, what is 1? AF is equal to C is equal to 4R. Here, that is according to equation 3, AF is equal to under root 3a square. Yes or no? So when we compare these two, what will we get? Yes, we will get 4R is equal to root 3a square. That will write once again here. Comparing 1 and 3, what did we get? 4R is equal to under root 3a square. Clear? We have arrived at this equation now to find A. So from this, what is A? Interchanging, we have root 3. Square root of A square will be A. So I can write as A root 3, isn't it? Is equal to 4R. From this, what is A? 4R by root 3. So we got A now. Next, volume of the cube, that is unit cell here, is A cube. What is A? Just now we got 4R by root 3 whole cube. That will be 4 into 4 is 16. 16 into 4 is 64. You have 64R cube. What is root 3 whole cube? It's not root 3 whole square. It is root 3 whole cube. So don't jump into conclusion. It will be root 3 into root 3 into root 3. Root 3 into root 3 is 3. This we will retain as it is. So it is 3 root 3. Okay. So here we can write 3 root 3. So this is volume of the cube. That is the denominator we got, right? Okay, let's proceed. What about the numerator now? What is the numerator? Volume of the n spheres, right? And how many spheres are there in BCC unit cell? 2, we know that. Yes. So volume of 2 spheres will be how much? How 2? You remember, isn't it? Because the corner fellow makes a contribution of 1 by 8. There are 8 such fellows. Therefore, 1 sphere due to corner position, and this fellow at the body center belongs completely to that unit cell. Therefore, that is 1. 1 plus 1 is 2. Remember? That means, yeah, we have 2 spheres. First of all, volume of 1 sphere is how much? That we know. 4 by 3 pi r cube. Right? Therefore, volume of 2 spheres will be 2 into this. That's all. That will be 8 by 3, isn't it? 8 by 3 pi r cube. So this is our numerator, right? Okay, let's proceed. Therefore, what did we get? The numerator, 8 by 3 pi r cube. What is the volume of the unit cell we got? 64 r cube, isn't it? By 3 root 3. 64 r cube by 3 root 3. This is the total volume of the unit cell we got into 100. Are you clear till now? Very good. Let's simplify it further. So this will be 8 by 3 pi r cube. You take the reciprocal. 3 root 3 will come to the numerator, and 64 r cube here into 100. Yes or no? Will we cancel out certain common things? Yeah, r cube will go. 3 and 3 out. And 8 ones are 8 eights are. So what is left out, my dear? Yeah. We got now. Look here. pi by 8 into root 3, isn't it? So, or I can say root 3 into pi into 100 by 8. Can we simplify further? You have to only calculate by substituting the value of pi, and if you multiply and divide, finally you will get the answer as 68%. What is the 68%? We have arrived finally at the packing efficiency in the case of BCC unit cell. So that means out of 100 volume or 100 units of the volume, 68 units of the volume actually are filled by the constant particles or the spheres. So what is the empty space in this case? 100 minus 68. Right. So that will come to 32, right? So 32% is the empty space, whereas 68% is the packing efficiency. What did we see in the case of simple? It was 52.36 we got, so 52.4, right? But this is 68. See, packing efficiency is more. That means right now you can come to one conclusion that PCC is more stable with higher packing efficiency than which one? Simple cubic lattice. Okay. Now the third one is, yes, packing efficiency in the case of CCP structure, that is, in other words, FCC. But please mind you, my dear friends, packing efficiency in CCP and HCP is actually same. So if you learn CCP as per the syllabus, it's quite enough now, because the same value will get for HCP also. Now let's see how to calculate the packing efficiency in CCP. Fine. So in order to calculate the packing efficiency in the case of FCC, just take a look at this FCC unit cell. Here, can you see the spheres present at the 8 corners, as well as the spheres are also present at the face centers? Can you see? Yes, my dear friends. But if you carefully observe, here also the spheres are not touching each other along the edge. Instead, you can see the spheres are actually touching along the face diagonal. Just have a look at it. Yes. Now, let's calculate. And please look at this image. So here we have highlighted, or we have focused upon the, yes, the face of the cube that is towards us or towards the front. Yeah. And as you can see, there are 4 spheres at the corners of that face. And of course, this represents the sphere at the center of that face. Okay. So if you see here, it's very, very clear that the spheres at the corners, this along the edge, are not touching. But as you can see here, the spheres at the corners and at the face center are touching each other. That means we need to consider the face diagonal. There is a diagonal passing through the face, right? The face which we have focused here. Okay, but why should we do all that? Yes, to find out the packing efficiency. And to find out packing efficiency, the denominator is total volume of the unit cell. For that we need A cube formula. For that we need A, isn't it? In other words, we need to calculate A cube. For that we want A. To get A, we can't take once again A is equal to 2R here. Right? Though we can consider this as the radius of the sphere, they are not touching each other, but they are touching along the face diagonal. Therefore, to find out A, we need to do something like this now. Yes. We have to join AC, that is a face diagonal. Are you here? And the face diagonal here is called as B. Let me write it for you here. It is B. And yes, my dear, there are 3 spheres along this face diagonal touching each other, of course. So this is the radius of this sphere, and this is the radius of this sphere. And from this point to this point, yeah, that is the diameter of that face-centered sphere, or that is given as 2R. Therefore, once again here B is equal to 4R. Okay, very good. But we have to find A, right? To find out A, we have to now consider the triangle, yes, ABC. Look here. This is a triangle We are now considering ABC. Once again applying Pythagoras theorem because it's a right angle triangle. Now I can say AC square, isn't it? That is the hypotenuse square is equal to what, my dear? AB square plus BC square. If BC is the edge, AB is also the edge that is given by A, because all edges are same and edge lengths are equal. So my dear friends, now I can say as per Pythagoras theorem, AB square plus BC square. Therefore from this, what is AC? Under root AB square. In place of AB square, can I put here A square? Yes. BC square is A square once again. In place of AC, I can put 4R, isn't it, from equation 1. Therefore, 4R equals, yes, under root A square plus A square is 2A square. Are you clear? Now, this can be written as, this implies that, root 2 into square root of A square. What is square root of A square? A. So, in other words, it's equal to A root 2. What is that? 4R. Remember that, okay? So, we can call that as equation 2, in fact. That's what? By comparing, I already compared. So, AC, in place of AC, we compared and we put 4R. Therefore, we have 4R is equal to A root 2. 4R is equal to A root 2. From this, what is A? A root 2 is equal to 4R. A is equal to 4R by root 2. Let's not simplify it here right now. Okay. So, this is our A. But what is the volume of the cube? Right? So, volume of the cube will be A cube, right? Means unit cell. In place of A cube, what can I write now? 4R by root 2 whole cube. That is nothing but, yes, 64 once again, isn't it? 4 4s are 16, 4s are 64 R cube by, what is root 2 whole cube now? It is root 2 into root 2 into root 2. Root 2 into root 2 is 2. So, this is 2 root 2. We'll put it here. So, this I think we can simplify here. 2 ones are 2, 32s are. So, this will be 32 R cube by root 2. What is this actually equal to? Volume of the unit cell. Okay. Let's proceed. In FCC, right, that is CC per HCP structure, how many spheres are there? 4, right? You remember how? Corner position, contribution is 1 by 8, so 1 by 8 into 8 is 1, and face-centered sphere will contribute half, and there are 6 such face-centered spheres at 6 face centers. Therefore, you get 3, 1 plus 3 is 4, right? Therefore, we got 4. And volume of one sphere we know is 4 by 3 pi r cube. And therefore, volume of 4 spheres will be 4 into 4 by 3 pi r cube. That will be 4 for the 16, isn't it? 16 pi r cube by 3. This is our numerator, okay? So, what is packing efficiency? We'll look at the numerator once again. 16 pi r cube by 3 we'll write. 16 pi r cube by 3 divided by, what's the total volume of the unit cell we got? Yes, 32 r cube by root 2. Here, we got this. 32 r cube by root 2. 32 r cube by root 2, right? Yes or no? Into 100. So, let's simplify this. So, let us simplify this. So, what do you get, my dear? 16 pi r cube by 3, reciprocal of this, root 2 by 32 r cube into 100. Okay. Let's cancel out the similar terms. R cube, we can cancel, right? And this is 16 ones are 16 twos are 32, right? Therefore, here you get, what is left out? Did you calculate? You're very smart. Pi root 2 is here, okay? Yeah, into root 2 into 100 by 3 twos are 6. So if you actually calculate further, you will get the answer as 74%. This packing efficiency in the case of FCC unit cell is 74%, means what is empty space? 100 minus 74. Isn't it? That comes to 26%. Yes or no? Okay, my dear. But I told you at the end, we will try to compare all and see which is more efficient now. Yeah. Before looking at the efficiency, we have to even look at the empty space, right? If the empty space is less, packing efficiency is more. We saw that, right? And if packing efficiency is more, I told you that the lattice will be more stable. So this tabular column shows us the different type of packing that is taking up different structures. That's what we saw: simple cubic cell, body centered, CCP and HCP, because I said both are equally efficient. And we took FCC for that matter. And we calculated just no packing efficiency of all these. We got 52.4% in simple, 68% in BCC, and FCC we got 74%. And when we subtracted these values from 100, we got the corresponding empty space in terms of percentage also. So from this, it's very clear that lesser the empty space, look here, lesser the empty space, higher the packing efficiency. And higher the packing efficiency, more stable is that lattice, okay? Got it? Yes. So friends, hope the session was very useful to you and you've enjoyed, I trust, okay, with a smile throughout, though there were so many calculations, but you're very smart, you're good in mathematics also. It's time for numericals and the topic is packing efficiency. Hope the concepts are quite clear and you remember all the formula, I guess. So let's not waste time. Let us take up the first question quickly. And the first question is, which of the following lattices has the highest packing efficiency? That is simple cubic, body-centered cubic, and hexagonal closed pack lattice. Yeah, this is from NCERT in text, question number 1.17. It's a simple memory-based question. I hope you remember. We already worked out the packing efficiency values. In simple cubic, we got obviously HCP. Okay. Okay, let's take up the next question now. Sodium metal crystallizes in BCC lattice with edge length of 4.29 angstrom unit. The radius of sodium atom is. The 4 options given. Let's not read all the options. Anyway, this question is from KSET 2015 question paper. Yeah, the data says edge length, that is A, is 4.29 angstrom unit. And we need to find the radius of the sodium atom. For that, try to recall the structure of BCC unit cell, please. Yeah. Let me draw quickly for you. Here, while explaining the packing efficiency in the case of BCC, I highlighted 3 atoms rather, 2 at the corners and 1 in the body center, because if you join from this point, okay, to this point, actually this is the body diagonal, right? And along the body diagonal, we saw, in fact, 3, 1 in the center and 2 at the corners. I'm trying my best to draw. All are not equal, just excuse me for that. Okay, anyway, I want to show that 2 at the corners, these fellows, and 1 at the center of the body, right? This one. So if you join their centers, you get the body diagonal. So if you call this as A and B, Say this is A and this B. So here AB is the body diagonal. And try to recall, guys. In fact, from here to here, this point to this point represents the radius of this atom, and from this point to this point, the radius of the other atom. From here to here, it is diameter of this body-centered atom, that is 2r. Therefore, r plus 2r, we got 4r, if you remember. Okay. Therefore, body diagonal is 4r actually. Please excuse me for this diagram. This is the best I could draw. Okay. But actually, refer the video where we have shown the perfect geometrical figure where you can see how body diagonal is equal to 4r. Okay. Anyway, let me continue here. Hoping that you have watched the video, you understand better here. Okay, my dear. We have proved that in BCC, 4r is equal to root 3 into a. Please do watch the video, then you'll understand how I get this relationship. Okay, we took two right angle triangles and we went by Pythagoras theorem and we derived. So I can't do it here possibly because it will take a lot of time. Watch the video, it will be very easy. That's it. Now we have to find r. Okay, so from this, what is r? R is root 3 into a by 4, isn't it? Let me write neatly. Root 3. Okay. Yes. That means r now is equal to, what is root 3, my dear? I think it is 1.732. Check it. Into a is 4.29 angstrom given, divided by 4 as per the formula. This comes out to be, if you calculate, 1.857. Okay. I have done it, so you also try once. So this is the right answer. 1.857 angstrom unit. Okay. Shall we take up the next question now? Yeah. Edge length of a cube is 300 picometers. Its body diagonal would be 600, 423, 519.6 picometer or 450.4 picometer. This question is again picked up from KSET 2018 question paper. Once again, edge length is given A, 300 picometer. And this what type, my dear? And they've asked body diagonal. Body diagonal means obviously it's BCC lattice because there we have, just now I showed, isn't it? Body diagonal is 4R. Yeah. Because along the body diagonal, 3 atoms are touching each other and hence you get 4R. So the question is, what is body diagonal? So 4R, the formula, is equal to root 3 into A. You don't have to take a radius here. So directly you can say body diagonal only. So body diagonal BD, let us say, is equal to root 3 into A. Simple substitution. A is 300 picometer. Okay, that is root 3 is 1.732 into 300. I think that comes out to be 519.6 picometer. Please try it, you'll get it, okay? That is body diagonal. Okay, so the right option is C. Right? Shall we go to the next question now? The packing efficiency of the two-dimensional square unit cell shown below is. Look at the diagram, and this is picked up from IIT 2010 paper, isn't it? Yeah. Okay. Two-dimensional, this is the keyword. Generally, we miss out that. It is two-dimensional square unit cell. That is the main clue there, in fact, okay? Because generally packing efficiency we have learned in the case of cubic systems, that is simple cube or BCC or FCC. But this is square unit cell, point to be noted, and it's two-dimensional, obviously. Okay, in that you need to find packing efficiency. That's why it's an IIT question, okay? So you should enjoy solving such tricky questions also, okay? And there are 4 options. Let's not look at the options now. Let's look at the solution. Okay, first of all, what is the formula of packing efficiency, my dear? In general, Even if you take a cubic system, yeah, packing efficiency is, yeah, it is actually total volume of the unit cell, right? Correct. So here also unit cell is, yeah, here also it's unit cell only. Total, yes. Now the question is volume or area. If it is a cubic unit cell, it is volume, but it is square unit cell. Therefore, you can't take volume, it is area because it is two-dimensional. If it is three-dimensional, obviously you have three dimensions. That is length, breadth, and height. In the case of cube, all three are equal. Therefore, we get a cube. That is edge length into edge length into edge length, isn't it? But here it's area. So total area of the unit cell is a square unit cell, of course. And the numerator, it is the area of n number of spheres or atoms, you can say, but here they are circles, they're not spheres, okay? Yeah, we'll say atoms, just circles, circular in nature, into 100 because we need to express in percentage. Very good. So this is the formula we need to use now. All that you knew was total volume here and here volume. That's all. Instead of volume, you're taking area because it's two-dimensional, the two square unit cell. Therefore, now let us take the, yeah, there's a side, right? The square. So all four sides are equal. Therefore, let's call this as A. If this is A, this is also A, this is also A, this is also A. And here there are four atoms at the corners and one in the center of the square. So now if you see the contribution of each atom at the corner is 1/4. Look, only this portion, right? Yes or no? Only this portion belongs, right? Look, isn't this 1/4 of that circle? Of course, yes. So there are four atoms at the corners, each, okay, four atoms at the corners, okay, and the contribution at corner is, yeah, 1/4. It's not 1/8. So it's not 1/8, it's 1/4 because 1/4 of that atom belongs to this square unit cell. Can you see that? This is outside, it is just that 1/4. But how many are there? Four. Therefore, number of atoms at corners. Why am I doing this? Because I need to find this n. To find n, I should know its position. Okay, where are they? Corners, and also in the body center. Okay, so first of all, number of atoms due to corner positions. So how many are there? Four, isn't it? So therefore, number of atoms at corners per unit cell will be 1/4 into 4, that is 1. So due to corners, we got 1. Now due to body center, we know the entire thing belongs, isn't it? Therefore, it's only 1. So 1 plus 1 is 2. So we got 2 here. Now we need to find area of 2 atoms. I mean, all the atoms are circular in nature. They are circles, right? And what is the area of a circle, please? Pi r square. Okay. So area of one atom is pi r square. But here it's area of 2 atoms we have. Here 2. Therefore, it's 2 pi r square. Clear till now? May I rub this part? Okay, hope you made a note. Fine. Now, we got the numerator. So here, packing efficiency is equal to 2 pi r square by, we need to find the total area of unit cell. What is the area of unit cell, please? It's actually a square, isn't it? Because it's square, a into a. Okay. But how do we find the packing efficiency? For that, we need to find a first, isn't it? Okay, to find a, what can we do? It's a square. And we know these two sides. So shall we join this point and this point now? Okay. When we join these 2 points, let me take red only. When I join these 2 points, you get two right angle triangles. So applying Pythagoras theorem, we can find the diagonal now, because diagonal is 4r. Why? Because from here to here, this is radius of this atom. Here to here, the radius of another atom. This is diameter, that is 2r. So actually, this diagonal is 4r, isn't it? So if you call this as A, B, C, here AB is a diagonal, that is 4r. Applying Pythagoras theorem, in fact, in this right angle triangle ABC, this is the hypotenuse. Therefore, we have now AB square is equal to AC square plus BC square. And AB square is what did I say? What is AB? 4r. So 4r square is equal to AC. Yeah, AC and BC both are A, because both are the same sides, equal sides rather. So it is A square plus A square. That will be 2A square. This is 4r square. Okay, whole square, mind you. From this, can we find A? It's very simple. So 4 square is 16. 16r square is equal to 2A square. Okay, from this, once again, A square is equal to 16r square by 2. So 2 ones are 2 8s. So now in place of A square, I can put 8r square, right? So now here we have 2 pi r square by, in place of A square, 8r square into 100. Are you clear? Very good. So we can cancel this. R square and R square. 2 ones are 2 4s are, 4 ones are 4 25s are. And if you multiply now, we have packing efficiency is equal to pi, that is 22 by 7 into 25. You multiply this, you will get 78.54. So the right answer is D. Okay. So we have come to the end of this problem solving session. Hope it was very useful. Please try some more problems so that you can really try very, very well in the exams also with the same ease. Okay. So with that note, thanks for watching. Bye-bye.